All right, so continuing with this lecture, we're going to go ahead and talk about period and frequency in oscillations. So periodic motion is a motion that repeats itself at regular time intervals, such as an object on a spring moving up and down. So if I move a spring, okay, so say I have a spring, and I place an object here, okay, and then I displace this spring going up, say, okay, that spring is now going to, I'm not very good at drawing, but it's going to displace itself upward, okay, so that object will be upward, and then eventually it'll go downward and so forth, okay. So that's the idea of this periodic, motion, okay. I accidentally pushed pause on the thing here, but let me erase this. Okay, so a period, or T, is a time to complete one oscillation, and the frequency is the number of events or oscillations per unit time. Okay, so a period would be something like, if this is one motion, the period would be the time it takes for that entire oscillation to complete. And the frequency is going to be the number of events or oscillations per unit time. Okay, so if this is one oscillation, then that's going to be one per, I don't know, say second. Okay, and to connect these two, there is this formula where frequency F equals 1 over T, which is the period. Okay. So the units, the units for period is in seconds, and the units for frequency is going to be in cycle or oscillation per second. Okay. And so it can be 1 cycle per second, or it can be just 1 over seconds. And we define that as a hertz. Okay, so 1 hertz. Hertz. Okay, like the car company. Okay, so that's going to be your units of frequency. It's going to be in hertz. So let's go ahead and look at an example now. Okay, example 16.3. We can use the formulas presented in this module to determine both the frequency based on known oscillations and the oscillation based on a known frequency. So let's try an example of each. A medical imaging device produces ultrasound by oscillating with a period of 0.4 milliseconds, okay? What is the frequency of this oscillation? Okay, so again, we know the period is equal to 0.4 milliseconds. Okay, so this sorry, my dog is barking at me. This mu here is indicates 10 to the negative 6. Okay. So that would be, I believe it is a microsecond. And so we can go ahead and just note that for a second here. And we want to know the frequency of this oscillation. So we just learned, I'm going to go ahead and erase that. We just learned that frequency is equal to 1 over my period. Okay, so I can go ahead and plug that in. So 1 over the period is 0.4 times 10 to the negative 6 seconds. So my frequency, if we use a calculator, 1 over 0.4 times 10 to the negative 6, that is going to be 2.5 times 10 to the 6 now. And this is again in hertz. Whoops. There we go. Okay. Or we can say 1 over seconds. Same thing. Okay, so that is part A. Now looking at part B, it's asking the frequency of middle C on a typical musical instrument is 264 hertz. What is the time for one complete oscillation? Now remember that one complete oscillation is going to be the period. So using this same formula, we can solve for our period, t, and so that is going to be equal to 1 over my frequency, right? Okay, so let's go ahead and plug this in. It's going to be 1 over 264 hertz, okay, or 1 over 264 1 over seconds, whichever way you want to look at it, okay? So again, using our calculator, saying 1 over 264, I get a period of 3.79 times 10 to the negative 3, and this is now in seconds, okay? So this is my period of oscillation. All right, so give me one moment and I'll be right back. Okay, so we're going to go ahead and continue now into simple harmonic motion. So the idea of simple harmonic motion is that it is some kind of oscillatory motion for a system where the net force can be described by Hooke's law. Okay, and such system is called a simple harmonic oscillator. Now I need to define a couple of things first. One thing is called the amplitude. It's indicated by a big X or a capital X, and that is the maximum displacement from an equilibrium. So if I'm looking at a wave, something like this, okay, my amplitude would be from this point to this point. Okay, so it's my max displacement from my equilibrium, which would be this here. Okay, so that would be my capital X, my amplitude. And in this simple harmonic motion, or SHM, the period and frequency are independent of that amplitude. So we need to now define period and frequency in this simple harmonic motion. And this is how we do so. Okay, we have our period equals to 2 pi square root of the mass divided by the constant here, the force constant. Okay, and F then, or the frequency, remember that period is T, frequency is F, is going to be 1 over this T, 1 over T, and so it's 1 over 2 pi times the square root of K over M. Okay, so we're going to use this idea in calculating a couple of examples. So in this example, 16.4, we want to calculate the frequency and period of these oscillations in a car. So the question states, if the shock absorbers in a car go bad, then the car will oscillate at the least provocation, such as when going over bumps in the road and after stopping. Calculate the frequency and period of these oscillations for such a car if the car's mass, including the load that's in it, say a person, is 900 kilograms. And the force constant K of the suspension system is 6.53 times 10 to the 4th Newton over meter. Okay, so again, we want to calculate the frequency and the period. So let's go ahead and calculate the frequency. Okay, so the frequency we just found has this relation. It's going to be 1 over 2 pi times the square root of K over M. Okay, and we could double check that. Yes. Okay, So we can just plug in our numbers here. 1 over 2 pi square root of k, which is 6.53 times 10 to the 4th Newton over meter, divided by 900 kilograms. Okay, and so you can put that into your calculator. Whoops. So I have 6.53 times 10 to the 4th divided by 900. Take the square root of that and times it by 2 pi. Or actually, whoops, we want to divide by 2 pi. So do that and then divide by 2 pi. There we go. So I get my frequency is 1.36 hertz. Remember, frequency is in hertz, or 1 over seconds. Okay. Now, what is this frequency? This is going to be the frequency of these shock absorbers. Okay, so how many times per second do these oscillations happen? So say from this peak to this peak. Okay, and now our period, we can use the same equation that, or a similar equation that we just used. So 2 pi square root of m over k. But we also know it is just the inverse of f, the frequency. So we can say this, 1.36 hertz, and calculate that. And we get 0.78, 0.738. Sorry about that. And this will be in seconds because this is a time. Okay, so this is how we would calculate the frequency and period of oscillations. Okay. All right, so moving forward, we want to be able to describe the simple harmonic motion in terms of equations. And this is done through kind of putting them into a type of wave motion. Okay, so kind of translating it. And so we can do this through the use of a few trigonometric functions. And those functions are cosines and sines. Okay, so hopefully you remember this from maybe some algebra or pre-calculus, or I think algebra, that cosine and sine, these are wave equations, okay? And so these are the way that we can describe this motion, okay? So for a position, so this first one is position, at some time, that is going to be equal to an amplitude, cosine of 2 pi t, which is the time, over the period. Okay, the velocity at some time is equal to negative v max, and I'll say what v max here is in a second, times sine of 2 pi t over the period. Okay, v max is the maximum velocity. Okay, and that I believe it describes a bit more in the book, but for now we can just say this is v max. And then we have the acceleration at some time t is equal to negative k times the amplitude over the mass times the cosine of 2 pi t over the period. Okay, and I have put down here what the acceleration is. So we just want to note that acceleration in general is equal to F over m. That was given to us by Newton's second law. And then the force in this type of motion is k times the amplitude. So this is just another way of saying the acceleration. Okay, so we're going to continue this in the next video.